In this example, we are given two identical bars which are connected by an ideal spring of natural length L0. It is also given that its force constant is K as shown, and a constant horizontal force F starts acting on one of the bars as shown. We are required to find the maximum and minimum separation between the bars during their motion. We just analyze this situation. We can see initially the bars are placed at the natural length of a spring, that is L0. So if the force is applied, the length will increase. That means the minimum separation during motion of the two bars we can directly write as L0. So one answer to this problem we can directly write, that is minimum separation, which will be equals to L0. Another point is how to calculate the maximum separation. So we can state, as it will start moving, first this second bar will move, and then due to elongation of a spring, first bar will also start moving because the spring will exert a force on it. It is advisable to handle all such type of problems in the reference frame of the center of mass of system. Like here we can see acceleration of center of mass of the system we can directly write as F by 2m. Because we already studied in the topic of center of mass that center of mass acceleration is net external force divided by sum of all the masses. So it can be directly given just ignoring the spring, because the spring will exert an internal force or equal and opposite force on the two bars which will cancel each other. Now in this situation, with respect to center of mass, if we draw the free body diagrams of the two bars, we can write free body diagram of bars with respect to center of mass. We can see for the first bar, it will be experiencing a pseudo force with respect to center of mass, which is MACM. And for the second body, we can write it is experiencing an external force and a pseudo force small m ACM. As Kx, which is the force applied by the spring on bars, it is acting equal and opposite on the two. So with respect to center of mass, we'll ignore the spring force. So in this situation, with respect to center of mass, if we just have a look on the two, the first bar will be displaced toward left and the second will be displaced toward right. Say that displacements are x1 and x2. Then we can state whatever work is done by the forces in the reference frame of center of mass in displacing the spring on the two sides by x1 and x2. Total work done will be stored in the spring in form of its potential energy. So we can write by energy conservation MACM into x1, which is the work done by the pseudo force with respect to center of mass on bar 1, plus work done by another force will be F minus MACM into x2. This must be equals to half K into x1 plus x2 whole square. That is the total work done on the system by external forces onto the spring, we can say more precisely. So whatever work is done, that will be the gain in potential energy of the spring. On simplifying, say we'll be getting M into ACM, we can write as F upon 2M. So F we can take common. So it will give us M into acceleration of center of mass, we can write as F by 2M into x1 plus F minus M into F by 2M into x2 equals to half K x1 plus x2 whole square. Now in this situation you can see this M gets cancelled out. If we take F common on left hand side, it will be x1 by 2 plus x2 minus x2 by 2, that will be x1 plus x2 by 2. So here we'll be getting it F into x1 plus x2 by 2 is equals to half K x1 plus x2 whole square. This x1 plus x2 gets cancelled out. and 2 also gets cancelled out. We can see the value of x1 plus x2 here we are getting is only f upon k, which is the answer to our problem. So carefully you just handle this problem once again in your copy by your hand, and be careful in future also that whenever such type of problems are there which are also considered as spring block system with external forces, you should handle such problems always very easily in the reference frame of center of mass.